Okay, thank you, Francois, for the introduction, and many thanks to the organizers for the invitation to speak here. Yes, the Funk metric, let's start. K throughout the talk will stand for a convex body. So that's a compact convex set in Rn, typically with, well, always with non-empty interior for our purposes. And here comes a definition. So the Funk metric is a natural metric that's defined on the interior of the set. It is a non-reversible Finsler metric, such that the tangent pole at every point is the set itself. So I didn't prepare with a chalk. Luckily, they're all here. A Finsler metric is the same thing as a norm in every tangent space, which is the same thing as specifying a unit ball at every tangent space. Now we have K here, which sits in the affine space. You fix a point, and once you fix a point, it gives you an identification of your space with the tangent space. At this point, this being the origin, and now this is the unit ball at this point. So of course, while they look the same, since the origin moves around with respect to the body, it's not the same thing as a normed space. For instance, if you're close to the boundary, then this vector has a very serious norm that from the normed perspective you don't see. So it's a bit like hyperbolic metric in a formal way, we will see soon. Okay, I forget that this doesn't work. Okay, so of course this is an affine invariant construction, and you can go ahead and define the distance as you would in Finsler metric, and you will find out that it's given by this formula. So if this is x and this is y, and you want to compute the distance between them, you draw this interval, you extend it till the intersection, and the distance from x to y is just the logarithm of the ratio. Okay, and this metric is non-symmetric, of course. You can symmetrize it, and you get the Hilbert metric. It is more well known. It is given by half the logarithm of the cross ratio. This is W here. And the cross ratio, as you know, is invariant under collineations. It's a projective invariant. And so the Hilbert metric is a notion from projective geometry. Moreover, both metrics, the Funk metric and the Hilbert metric, are examples of what's called projective metric, which is something else. It means that straight segments are geodesics, are curves of shortest length. Okay, so here are some examples. If you start with a Euclidean ball or with an ellipsoid, then the Hilbert metric there is just the hyperbolic metric, the Beltrami-Klein model. Actually, the Funk metric is also not so different. What you get for the Funk metric in an ellipsoid is also the hyperbolic distance with a correction which is just, well, it's an exact form correction, right? So f is some function, and you have this this correction term. Okay, close to the hyperbolic metric. Also, if you look at the simplex for the hyperbolic for the Hilbert metric, you get some normed space, and actually that's the only case when you get a normed space. But more generally, if you look at polyhedra, then you get something which is by Lipschitz equivalent to a normed space. Somehow Hilbert metric and also Funk metric, they're very much dependent in their qualitative behavior on the regularity of the boundary. If you have something like a polytope, this is roughly a normed space. If you have something which is strictly convex, then it in some ways is closer to the hyperbolic space. Okay. We will be speaking about balls a lot in function geometry, and there's a nice feature to them. They're actually just homothetic copies of the body itself. So you have to be precise because the metric is non-symmetric. So we're talking about the outward ball. So all points which are start at the center go to X. And this is just a homothetic copy of K around the center with this coefficient, depending on R in this way. And we will need the notion of volume. We will be using the Holmes-Thompson volume, which is a general notion in Finsler geometry. In this particular case, it's going to be given by this density. So if you fix a Lebesgue measure on your space, then you also have the associated Lebesgue measure in the dual space, and then this product is independent of this choice of Lebesgue measure. So the density is just the volume of the polar body at this point. Yes? Make a well, sure. So if this is your center point and you want to draw a ball of radius 1/2, then you'll have to compute this number. Well, maybe radius, say 1. 1 is easier. 1 minus 1 over E. And then you will take this coefficient and draw something like this. So, it's just put in here, plug in here a nail, and then rescale K around this point. Okay. So the density of this measure is just the volume of the polar ball, of the polar body at this point. Of course, the closer X gets to the boundary, the larger the polar body is going to be, the larger the density is. Okay, and if you look at the volume of the ball, then what you get for a fixed radius is really a functional of K. You can think of it as a function of K, which is moreover GLN equivariant by construction. So that already tells us that we can look at things like maximizing and minimizing it because convex bodies modulo GLN are a compact set. So that's what we're going to do later on. So you can think, yeah, so if you fix the radius, then it is, and the center point, say, yes, yes. Mm-hmm. So more often than not, I will be restricting attention to centrally symmetric convex bodies, and then there is a natural choice of. Okay, a remark here is that in Finsler geometry, typically you have to decide between several reasonable definitions of volume, Holmes-Thompson being one of them, but you also have the Bussmann-Hausdorff definition. There's a few other ones. But here, at least, the Bussmann-Hausdorff doesn't make any sense because that would be just Lebesgue measure, the same Lebesgue measure you'll get on the norm space. It's not sensitive to the geometry at all. So Holmes-Thompson is really your best shot at relating volume to the distance. Okay, we'll be speaking about billiards a little bit. So a reminder, what are billiards? If you have a domain, well, in this setting, if you have a domain in the interior of K, and that's going to be your billiard table, then you're going to say this is K, and this is the domain, and you want to say that 3 consecutive points are an orbit of a billiard if the distance from here to here plus the distance from here to here, considered as a function of this argument, has a critical point there. That's not really how you play billiards. What you really want is to know how the ball will reflect. So luckily, that's a problem that has been considered by Gutkin and Tabashnikov. They considered general Finsler billiards. And in this particular setting, the reflection law looks like this. So you start at Q0, and you're going in the direction of P0. So those are points at the infinity. P0 is the direction, and you go and you hit at Q1. Well, what do? You draw tangent lines at Q1 and at P0, intersect somewhere. You draw the other tangent to the, well, the outer body, the one defined in the geometry. You get the new direction, P1, and now you go in this direction, and you hit well, what you hit. That's the reflection law. And one thing that jumps immediately to your attention is that this is projectively invariant, right? We're talking about lines, we're talking about tangency, nothing else. So indeed, it turns out that the Funk geometry is closer to being projectively invariant than what you would initially expect. Here is the statement. If you have a collineation, projective transformation, such, well, we're talking about bodies in Rn, so we want to make sure that the image is still a compact set, okay? And you have, so there's one convex body defined in the geometry, that's K, and then there's the billiard table. The billiard table does not need to be convex in principle. Yes. The convex body is all there is. That's your universe when you're doing Funk geometry inside K. Right, so if you have K and you have a transformation, then you can talk about two different metrics inside K. One is the one norm of Funk, the one we started with. The other one is the pullback of the Funk metric on the image of K. And you can think about both of them as functions on the tangent bundle, right? Every point, every tangent vector should give you a number. So the difference between them is actually an exact one form, and it's not hard to understand which form that is. So it's easier to speak about it in the following terms. If you fix one point in the dual projective space, well, one, say eta 1, then this is fixing the hyperplane at infinity in RPN that identifies the complement with an affine space. So if you have two such choices, that's like having two different Funk structures on a convex body in the projective space. So the difference between those two norms is given by this explicit expression. So you have to take a moment to see what's written here. Each eta defines a function on well, on the left-hand side by choosing some representative of a point on the line, which is eta. It's a point in the projective space. Okay, so this function really is defined up to a constant, which disappears after you take a logarithm and differentiate. So that's well defined. Okay, this immediately has some corollaries. For once, the Funk volume is projectively invariant. All right, you don't even need to know that this form is exact. It's enough to know it's a one form, because an addition of one form is the same as translating the cotangent unit ball. Doesn't change the Holmes-Thompson volume. But it's an exact form, so you also have those two corollaries. For instance, if you have a submanifold, then the geodesics on it are mapped to geodesics on the image by a projective transformation. And moreover, the length of closed geodesics would be preserved. And the same goes for billiards. If you have a compact domain, then billiard orbits correspond to billiard orbits, and the length of closed billiard orbits is invariant under projective transformations. So because when the orbit is closed, then you'll be adding up. You'll be integrating a closed one form over it. What is x? X is the point, right? It's a point in K, yes. So as a function of x, this ratio is well defined because x is a point in the projective space. So you can think about it as a point on as the ray in a linear space one dimension higher. And then doesn't matter which point you choose there, the ratio is well defined. Now the dependence on the etas, once again, you choose representative, so this is defined up to a constant, but this is already well defined. Okay, so then there's even another tighter relation to projective geometry. But for this, let's first recall some classical results of duality in convex geometry. So the first one goes back to Schaeffer in '76. So he considers symmetric convex bodies the unit ball of an actual norm. And he conjectured that if you consider the boundary of K in the norm space where K itself is the unit ball, so that's an affine invariant of, well, it's a Finsler manifold that's canonically, that's affinely attached to K, affine invariantly. And you look at the shortest closed geodesic, that's called the girth of K. He conjectured that K and K polar would have the same girth. He proved it in 2 dimensions. Then the first step in resolving this was done by Holmes and Thomson, who showed that those two manifolds have the same Holmes-Thomson volume. That's where the name comes from. And more recently, Holmes-Thomson. Oh, it should say volume. I'm sorry. It should say equal volume. Yes, it says length, but it should have said volume. Thank you. Sorry. Right, and more recently, the conjecture of Schaeffer was resolved. In fact, in the more general, there's the more general statement. If you have two convex bodies, and one time you consider the boundary of K inside the norm space where L is the unit ball, and the other time you consider the boundary of L polar inside the norm space where minus K polar is the unit ball, then they have the same Holmes-Thomson volume and the same length spectra, which is the collection of lengths of closed geodesics. So all of that. No, symmetry? No. To define the polar. No, the polar is the collection of linear functionals which do not exceed 1 on your convex body. There's no symmetry. He proved generalized. And there's another duality that's relevant. Goes to Gutkin and Tabashnikov. So if you consider the two billiards, okay, once again, K inside the space with L, the unit ball, and L polar with minus K polar, the unit ball, then there is a duality of the billiard orbits, the same. There is a correspondence of billiard trajectories. Closed orbits would correspond to closed orbits, and the length is the same for corresponding closed orbits. And here is how it works. Very briefly, this. So you go from Q0 to Q1. You hit at Q1. You look at the normal, and all this time you were going in the direction P0. So you knew you're standing here. So once you hit, you look at the normal. You go in the direction of the normal all the time while standing here. Okay. Now you hit this point, you have this normal, and you go in minus this direction because there's a minus, and this is how you can see the duality. What you see here with your eyes is the billiard orbit, but this kind of shadowy part is really just the dual billiard orbit. It's a billiard that's played in Minkowski in normed space. Minkowski space means the norm doesn't have to be symmetric, and playing billiard is by the same rule as before. You look for extremizers of the length functional. So, for instance, if T here is Euclidean, then you're playing usual billiard, and it's a nice exercise to convince yourselves that if T is the Euclidean ball, then what's described here is just the usual reflection law of billiard tables, incidence angle. Well, minus K, so K polar, so when you're playing billiard here, you're playing it, sorry, T is L. I borrowed this picture. So you're playing this T is L polar. You're playing this billiard inside L polar, and the geometry is given by K polar, by minus K polar. Okay, so you can measure distances. Well, that's how the duality works. Right, so that's the unit ball of this non-symmetric norm that you're looking at here. Yeah, well, I mean, I still haven't discussed the duality in Funk billiards, but yes, that's a limit case of Funk. So, yes, that's the picture in Funk. So let's be a bit precise. We'll be talking about projective polars, which is very much related to linear polar bodies, but here's the definition. If you have a convex body in RPN, then the polar body consists of all hyperplanes that do not intersect the interior of K. So that's a polarity thing. That's also a convex body. And we will also be making use of the reverse Funk metric, which is what you think it is. And here's how the Funk billiard duality works. So you're going from Q0 in the direction of Q0. You hit Q1, well, and you should decide where you're reflected. So you transfer yourself to the dual space. So all the time, you were actually standing at P0 because this is the direction you were traveling in. So P0 capital is the tangent hyperplane at the point P0. That's the relation between left and right. So you're standing here and you hit Q1. So this is the direction you're going to be traveling from because this is the reverse Funk metric. Now you're traveling from Q1 through P0. You hit the new direction. So P capital 1 is the tangent hyperplane to the new direction you're going to follow now. Yes? How convex should they be? Well, I prefer to assume whatever is needed for everything to work, but this is a discussion of the local reflection law, right? If you hit the wall, then you would know where to reflect yourself. Mm-hmm. Yes, of course. So clearly there can, sure. I do not want to discuss billiards and polygons. Of course. So just like in usual billiards, everything would be defined outside the set of measure 0, right? Mm-hmm. Okay, so this is the duality of the billiards, but actually there's more that holds. Here is the statement for the Funk metric. Unlike the Hilbert metric, it exhibits a projective duality. So here are the statements. We have now two convex bodies, K inside L. The first statement is that the volume of K inside L equals the volume of the polar of L in the reverse Funk geometry of K polar So I put here reverse func for moral reasons, but really there's no difference for the volume. You can just look at the func volume because that's the difference of the volume. Because the volume of a polar minus the polar is the same thing. Okay, but also if you look at the closed geodesics on the boundary of K, then they correspond to closed geodesics on the boundary of L polar inside K polar. Here it's important that you're looking at the reverse func metric, and they would have the same length. And the billiards we were discussing, same thing holds, corresponding billiard orbits would have the same length. And as was pointed out, in the limit when K is much smaller than L, what you're looking at is, it becomes Minkowski geometry, it becomes flat, and you recover Schaeffer's duality proved by Alvarez-Paiva and the Gutkin-Tabachnikov duality of billiards. So in the case of two periodic orbits, it's actually very easy to see that the orbits would have the same length. So let's consider it briefly. This is what a two periodic orbit looks like. It consists of two bounce points and two directions, such that all tangent lines meet at the same point, or tangent hyperplanes. Okay, then the func length here is really the Hilbert distance between those points, because you sum them in both directions. So this is the cross ratio of those 4 points, which is the same thing as the cross ratio of those 4 lines, which is the corresponding length in the dual space. But for more general orbits, it's not so easy. So periodic is a trajectory with 2 bounce points, which is periodic. So here is the idea. Well, here is a sketch of why there is duality of volumes. Maybe to introduce that's the easier one. So there will be a special set Z inside the product of the projective space and the dual projective space, consisting of that's the incidence hyper surface of points belonging to a hyperplane. And in its complement, it turns out there is a unique measure mu, which is invariant under the group of collineations. Yes? Unique octoscale, of course, and it's not hard to check that the func volume is of A inside the func geometry of L is just the measure of this product, A times the polar of L. And once you can write it explicitly if you identify, for instance, a projective space with the sphere given by this formula. You can go ahead and check that it's invariant. And written like this, it's completely clear that you have this duality, because the measure coming from projective space and the measure coming from the dual projective space, they must coincide up to a constant. You can check this constant as 1, and that's that. Okay, so for the billiard orbits, it's not much more difficult. Now it turns out that there is also a symplectic, a distinguished symplectic form on this product outside of Z. You can describe it, for instance, as some symplectic reduction, or in your favorite manner. And billiard orbits are related to the symplectic form, of course. So a billiard orbit corresponds to a characteristic curve. So a curve such that its tangent, its velocity vector lines at the kernel in the kernel of the symplectic form are restricted to the boundary of the Colbois bundle. And the key insight here is that you can identify the cotangent space where everything lives with a subset of this product. So somehow, instead of looking at dual vectors, you're looking at points in the dual projective space. And here everything becomes symmetric. And okay, and once you do that, so every billiard curve, you can lift it to a characteristic curve. The length of the orbit is the action of the corresponding lift. And because the symplectic form is essentially unique, the two one forms, they must differ by an exact form, and you would have the same length. Okay, so pretty standard proof once you once you see those identifications. Okay, so that concludes the projective geometry part, and now I'll be talking about volumes. Looking at volume of balls is interesting. Of course, as the radius, for small radius, we basically get the volume product. That's an interesting invariant in convex geometry that I'll be saying a few words about. At infinite radius, which is probably more interesting for differential geometry, in the large, certainly, we have we have asymptotic. So for instance, when k is sufficiently irregular, this is not the most general thing you can assume, but let's keep it simple. The volume behaves exponentially, that's the power, and there's a certain coefficient, which is a known invariant in convex geometry. It's called the center affine area of k. It's given by a certain integral of the Gauss curvature at the 1/2, and here you have the support function to some power. Something, doesn't really matter what, it's a GLN invariant. It has been shown by Monica Ludwig to be essentially the unique GLN invariant valuation under some regularity assumption. Okay. No, but because you're forgetting about a factor of 2. That will be, I will explain it in a couple of slides. Right, so the volume product in convex geometry, for our purposes, let's define it as follows. We will be looking at polar with respect to the point x in the interior, and then we will be minimizing over all such x's. So it's well known that there is a unique point which minimizes. It's called the Santalo point of k. So a famous theorem is that this volume product, thusly defined, is uniquely maximized by ellipsoids. And then we have also this other inequality, the center affine isoperimetric inequality, which says that if you look at this coefficient we had before, which appears for the volume of the ball of large radius, and you minimize that over all points in the interior, then this also is uniquely maximized by ellipsoids. And so it's natural to conjecture that for any given radius, if you minimize this volume over the center points, this functional of k will be uniquely maximized by ellipsoids. So, that's a conjecture. What is it related to? So, for instance, there's this conjecture of Colbois Verovic, which was proven fairly recently by Tholozan and also by different methods by Vernicos and Walsh, which looks at the entropy, the volume growth. You take the logarithm of the volume of this time it's Hilbert volume of Hilbert ball of large radius. So statement is that the exponent is no greater than n-1. That's a theorem now. And in fact, if you assume some regularity, then you can be more precise than that. But then, well, if the body is sufficiently regular, then the exponent is exactly n-1, and then you can start looking at the coefficient, how it depends on k. And in this case, theorem of recent theorem of Vernicos and Young, that this coefficient, which is called the central projective surface area, because it comes from the Hilbert metric, which is projectively invariant, slightly different integral. This coefficient is uniquely maximized by ellipsoids. Okay, so this is all the evidence we have for the validity of the Funk-Blaschke-Santalo conjecture. Now, let me point out that, in fact, if you do prove Funk-Blaschke-Santalo, then you can recover this theorem, and in fact, in a sharper form. Here is why. So due to this inequality between the Hilbert distance and the Funk distance, there is this inclusion of Hilbert ball inside Funk ball, so that should answer your question. And then you can relate also the volume densities by some well-known convex geometric inequalities, Roger Shepard. And so you can bound the Hilbert volume of the Hilbert ball by the Funk volume of the Funk ball. And then if you know that the maximizer of that is the ellipsoid, then this is something very explicit that you can compute and see for yourself. Yes? It's my conjecture. Okay, and here is what I can prove about this conjecture. So for this, I need to recall the notion of unconditional convex body. That's a convex body which has a group of symmetries, namely you can reflect it with respect to all the coordinate hyperplanes, and it is invariant, and the Funk-Blaschke-Santalo conjecture holds for this bodies. That's something you can prove with uniqueness of ellipsoids. So in particular, you recover the Colbois-Verovic conjecture for unconditional bodies. So the proof is far more elementary than Tholozan's original proof, and also the proof of Vernicos and Walsh. Okay, so here is another small evidence for the validity of the conjecture. So I'm getting a little bit ahead of myself, but if you accept for the moment that for polygons in the plane, you have the following asymptotics. So this time, it's not exponential, it's polynomial, it's quadratic, because it's a polygon. So the leading coefficient just depends on the number of sides. And then first coefficient is the first thing that actually depends on the geometry of the polygon. And here we can prove together with Konstantin Vernicos and Cormac-Walsh that if you minimize that coefficient over all center points, then this is maximized by the M polygon which is closest to being round, namely the regular M polygon, the fine images. Great. Okay, now let me say some words about the minimum of all of that. So the minimum is generally harder, so known as the Mahler conjecture, that the volume product of a convex body is minimized by the simplex. This, to my knowledge, is only known in the plane in full generality. In the symmetric case, a little bit more is known. For instance, so in the symmetric case, the conjecture is that it's minimized by the cube. But actually, that's not the unique minimizer. Here is a definition. A Hanner polytope is a polytope that is either an interval or a product of two Hanner polytopes or the polar of a Hanner polytope. It's a recursive definition. But anything you can get from intervals by taking products and polars. And it's easy to see that all Hanner polytopes have the same volume product, and the conjecture really is that Hanner polytopes are the unique minimizers in the symmetric case. So this conjecture is known up to dimension 3, and that's a fairly recent development, dimension 3, by Uri and Shibata. And there are various families of convex bodies for which one knows the conjecture. Notable examples are unconditional convex bodies, Saint-Ramond, zonoids, and polytopes with a few vertices. Yes? Octahedron is the right word, yes. Okay. yes, those are the two options. Okay, so if you look at the Funk volume, then you will realize it has two fundamental properties. One is multiplicativity with the right coefficients. You take Cartesian product; it's essentially the product of the volumes of the Funk volumes, and also it follows from the duality we discussed before that you have invariance to duality. So maybe it's you have to stop for a moment because balls don't correspond to balls, but since balls are under duality in general, no, sorry, I don't want to say that. Balls do correspond to balls because they're homothetic copies of Q. So it's perfectly. So this is an immediate consequence of the duality we had before. And so it follows that also for the Funk Mahler, for the Funk volume of balls, all Hanner polytopes have the same volume. And so it's natural to conjecture that for any fixed radius, this volume is uniquely minimized by simplices in general or by centered Hanner polytopes among centrally symmetric convex bodies. So notice that, at least in general, I don't need to say anything about Q, because if Q is not chosen to be the minimum point, then it's only larger. So yeah. And here again, what we can prove is that for unconditional convex bodies, the conjecture holds. And we have uniqueness of minimizers. They're the Hanner polytopes. Okay, and in the remaining time, I will actually discuss a little bit what happens in polytopes. So just a reminder, a flag in a polytope is, I talk about full flags, so it's a chain of a vertex contained in an edge, contained in a two-dimensional face, and so forth. So that's a flag. And it's been shown by Konstantin and Cormack that if you look at large radius asymptotics inside the polyhedron, for the Hilbert, in the Hilbert geometry, the leading coefficient is just the flag number, the number of flags of the polyhedron. And the same thing holds also for the Funk geometry with essentially the same proof because the Holmes-Thompson volume is projectively invariant, so it's pretty much the same reason. So you can think of the flag number as a combinatorial analog of center affine surface area. And I won't explain what's written here, except then saying that it also plays the role of other invariants in convex geometry. For instance, here, if you look at the floating body, then it appears where normally the affine surface area of a smooth convex body would be. So the flag number seems to play different roles, and it's an insensitive invariant. It only depends on the combinatorics. So, okay, hold this thought. What can we do with this knowledge? So, the flag number is obviously minimized by simplices as the smallest possible n factorial number of flags of any polyhedron in dimension n. But if you switch to centrally symmetric ones, then the minimizer of the flag number is not known. That's a conjecture due to Kalai. That the flag number is minimized by the cube, or actually by all Hanner polytopes of the same flag number. That's known, for instance, for simplicial polytopes, but not in general. There's another related conjecture which actually just adds up the number of all faces of all dimensions. That's the more famous conjecture with the same conjectured minimizers, also mostly open, this conjecture. Okay, so since we know the Funk-Mahler conjecture in the unconditional setting, we can recover, we deduce the Kalai conjecture in the unconditional case, but unfortunately, because we pass to the limit when r goes to infinity, we lose track of equality cases. But we are able to do a little bit nevertheless. I will explain that in a moment. And here, for contrast, there is this very recent result proving the other 3 to the n conjecture, also in the unconditional setting. Okay, so now we'll be talking about the second coefficient in the volume development. So for this, I need to recall the notion of a monodromy of a polytope. So when you have a flag and you fix some index I, then there is exactly one other flag in your polytope which coincides with this flag except at I, right? It would be helpful for me to draw a cube. I will draw a cube. So if you fix this flag, this point, this line, and this face, then for instance, for this face, there is exactly, for this flag, and if you fix this I equals 1, so the one-dimensional edge, there is exactly one other flag which shares this vertex and this face, which would be the same flag with this edge instead. So the I flip is the transposition on the set of flags, which replaces one flag with the other. That's our I. And the monodromy group is whatever is generated by all the I flips. And the one element we will be interested in is the complete flip. Is the composition, well, from right to left of R0, R1, R2, and so forth. So for instance, for this flag, first I would replace this vertex with this vertex, because I'm okay. And then I would be replacing, well, this edge with this edge. And then I would be replacing this face with this facet with this facet. And that's the new flag I have arrived at, having performed a complete flip of my original flag. And here is the two-term asymptotics. So the first coefficient is the flag number, and we have seen. And the second one sums over all flags of the manifold, this expression. So here we have a logarithm. Okay, so this is a flag, and now this pairing here stands for applying this linear functional. So an n-1 face in a flag is a vertex in the dual polytope, and then you can pair them. So that's the meaning of this pairing. Yeah, so that's a long and tedious computation, and there is some almost miraculous consolation going on, but I don't have much insight yet. But it is, you get this combinatorial invariant, and it immediately allows you to deduce something about the equality cases in Kalai's conjecture for unconditional polytopes. Well, let me explain that because fits the time. So for instance, if you have an equality case, so you have a polytope with a flag number the same as Hanner polytope, well, then definitely the first coefficient must be greater or equal to the one of the Hanner polytope, because if it were smaller, it would violate the known equality cases for finite radius. There would be some large radius for which it would be violated. So you must have that. But on the other hand, if you look at this coefficient, it's clear that Hanner polytopes actually maximize it because they give value of -1 for this pairing after, well, it's clear once you spend 5 minutes thinking about it. It maximizes it, and therefore you must have equality, and that immediately it immediately translates to a combinatorial effect. So here is what you get. If P is unconditional with minimal possible flag number, then for every flag, if you apply the full flip to this flag, then minus the vertex is already in the n minus, in the facet of the resultant flag. So while it does make the Politov very symmetric in some sense, with some strong restriction, but that's not, it does not imply 100 Politov. There is a larger class of two-level Politovs which definitely satisfy this condition, and we don't really know how much larger the class is. Okay, let me skip this. Well, let me skip everything else, and just spend 1 more minute. I'm sorry for wild speculations. So there is another conjecture of Kalai that there is a relation between this flag number and the volume product, this inequality. So this would be a consequence of this reverse Bishop-Gromov type conjecture that the volume of the ratios, the ratio of the volumes of two balls of different radius is minimized by 100 Politovs. Of course, we have no idea how to prove such a thing, but that would be a consequence of it. So if in the limit when one radius is small and the other is big, you recover this one. Of course, it's maybe one would first conjecture that a usual Bishop-Gromov inequality would hold with the ellipsoid extremizing in the other direction, but this is false. So that if you look at the behavior near zero, you differentiate, you get some inequality, which has been conjectured for some time, been unknown. It would have been far-reaching implications in convex geometry, the slicing problem, but it was shown to be false by Clartek. So at least the direct Bishop-Gromov is false. And we don't really know what's valid for the reverse. For instance, it would imply this inequality. I don't know about the validity of this inequality. Yeah, so I'll stop here. Thank you very much.